So, good afternoon, everyone. Myself, Shanmugaraj, and my research supervisor is Dr. Raphael, and we are from Indian Institute of Technology, Madras. And the title of my paper is Buildability Assessment of 3D Printed Concrete Elements through Computer Vision. So, as you know, the basic differences between a concrete 3D printing and a conventional construction is that thin layers of concrete is being extruded without any formwork. Hence, any minor variations in the process or the material properties will lead to the quality defects in the output. So, coming to the quality assessment in the present literature, there are three different stages where quality assessment is done. So, before printing, during the printing process, which is real time, and after the printing process. So there have been many studies which actually done before the printing process, which is basically to study the feasibility of how many layers can be printed. But the problem is there is always an overestimation or underestimation, and not all the input parameters can be modeled perfectly. So coming to the post-print defects, most of the post-print defects will lead to the corrective technique, but it will not be a preventive technique. And also the methods used are computational and monetarily expensive. So coming to the real time, there are like few studies, but the problem is most of the studies are focused on finding out only the anomalies. But what to do with the anomalies? So what I am trying to do is to generate these anomalies or to identify these anomalies and try to predict the properties like structure, buildability, and the extrudability failures. So this is my focus of the study. So coming to the buildability, buildability is nothing but the ability of the concrete. Once it is extruded, it should be able to carry its own weight and also the weight of the subsequent layers which are printed above it. If the concrete doesn't gain strength in within a certain time, the concrete will, before it's reaching its target height, it will automatically collapse. So currently this is kind of a trial and error. Most of the places, due to the difference in material properties, there are like a lot of failures like this. So what I'm trying to do is to put up a 2D vision camera and try to assess this buildability failure and try to predict it before it is happening. So coming to the buildability failure, this is a schematic of how the layer compression happens. So the bottom layers, if the concrete doesn't gain strength, it is going to compress. In case of a stable 3D printed element, so this is the cross-sectional view from the side of the 3D printed layers. As each and every layer is getting printed on top, you can see that for a stable element, the bottom layers doesn't compress much. But in terms of a failure model, a buildability failure model, you can see that the layers are continuously compressing. So what I'm trying to do is through this vision, 2D vision camera, I'm trying to create a image crop window. So you can see that this is the image crop window for layer number 3. You can see that since it is a stable element, the number of dimensional variations within this window is very minimum. But in case of the bottom element, you can see that within this crop window, you can see that the dimensional ranges are very high. So what I am trying to do is within this crop window, I am trying to identify the layer thickness and how it is varying from this point to this point as each and every layer is printed on top of it, and also the surface textural variations on the surface textural variations from this point to this point. This is what I'm trying to do. So coming to the next slide. So for the experimental prints, what I did is, so as I told, this buildability is directly dependent on the strength gain of the concrete within a certain time. So to vary the strength gain, I actually changed the workability values. There is, for every 3D printed element, there is an optimum range of workability where both buildability and extrudability is satisfied. So I have kept a higher workability value, medium workability value, and lower workability value. And also I'm varying the time of printing. So time of printing is nothing but the time from the point of mixing of water to the concrete to the point where you are trying to print. Okay, so I am trying to vary this also, and I am trying to take multiple cases. For each and every case, I am trying to create 3 different prints. So ultimately around 30 prints I have done. From this, I am trying to get the output. So the target I am keeping is I want to print 500 mm length. So if I'm able to print 500 mm height of 3D printed element without it is getting collapsed, it is called as a buildability, like good buildability, or if it is failing, I'm calling it as the bad buildable element. So this is how the 3D printed layer. So when it is having low strength gain, which is very high workability value, you can see that with a retention time of only 10 minutes, you can see you can get only 10 layers and it collapses after that. But in case of 25 to 30 minutes, that is after 25 minutes of mixing of water, you can see you can get around 23 layers, but it ultimately collapses. But after 40 minutes, you can get a good quality print, which is stable and it reaches 500 mm. So similarly, this is for medium quality, medium strength gain. In terms of medium strength gain, we are getting good quality, I mean, stable elements in terms of 10 minutes and for 25 minutes. But 40 to 45 minutes, what happens is the hydration comes into the play. The hydration of concrete comes into the play. The concrete becomes more coarse and it cannot be extruded through the nozzle at all. In the similar way, if you go to the lower strength, I mean, lower workability value, that is high strength gain, can see that in 10 to 15 minutes you can get a stable element of 30 layers, but 25 minutes and 40 minutes you cannot extrude the material at all. So this is how it works, and this is the methodology that I'm using, which I will be explaining in the subsequent slides. So this is the input image. From this input image, I'm using a salient object detection method, which is a deep learning based U2net architecture to actually predict the salient objects, that is the printed element. And from there, we can able to extract this only the 3D printed element. From this 3D printed element, I'm using Huff transform to identify the layer boundaries. From this layer boundaries, I'm able to get the individual crop window for each and every layer. So this crop window I'm maintaining for one particular layer, as subsequent layers are printing on top of it. So coming to the layer thickness measurement. So this is the GIF showing that as each layers are getting printed. So this is the one layer image window that I have taken. So within this image window, this is the layer 3s of image window of a collapsed element. You can see that as each and every layer is getting printed on top of it, the layer compresses gradually, and eventually the top layer is also coming into the picture. So what I'm doing is here, it is very clear there is a layer boundary and color contrast is there. So I'm using thresholding and canny edge detection methods to identify the layer thickness across 30 different sections of this thing only. So when I plot it as a graph, the first line on the top shows that the layer thickness across 30 different sections. So these are each and every 30 different sections when no layer is printed on top of it. So as each and every layer is printed on top of it, you can see that the line slowly comes down. But after some point of time, the layer thickness reduction is maximum, and ultimately after this line, that particular element collapses. So and in case of a stable element, so this is for a stable element, you can see that this is the first line. The top line is the layer thickness across the sections in the first instance. But as multiple layers are printed on top of it, also you can't see a major difference in the layer thickness. So by comparing this, identifying this layer thickness changes, when the layer thickness deformation is very high, we can able to say that it is a collapsed element. If it is less, it is a stable element. Similarly, I have done for surface texture also. Due to time, I will not be explaining the mathematics involved in it. But ultimately, I want to say is that, so surface texture, I'm using entropy. Entropy standard deviation is here. What it means is that the overall changes in the surface texture within that crop window. So for a collapsed element, there is going to be a lot of changes within the crop window. So the entropy standard deviation is going to be high. That is the overall surface textural changes. So for every collapsed element, I can say is that entropy standard deviation is very high. But in case of a stable element, the entropy standard deviation is very low. You can read more about that in my paper. Because of time constraint, I'm not explaining it. So coming to the final limiting value identification. So what I did is I have done around 30 prints. So for each print, the bottom 10 layers I'm taking. Bottom layers 1 to layer 10. And I'm trying to identify for each and every layer what is the entropy standard deviation, that is the overall surface texture changes that is happening within that layer, and also layer thickness changes that is happening within this layer, and I am taking it as individual data point. So what all these data points include is that these are all failure. These are the individual failure data points of individual layer data points of all the failure models. These are stable models. So what I can see is that I can find a decision boundary which states that if the the surface textural changes is beyond 0.065, that means a large amount of variation in texture is there, means it is a collapsed element. But if the surface textural changes are less than 0.065, it is more of a stable element. And in the same way, in case of layer thickness deformation, can find that most of the stable element data points are lying within the 12.5% of layer deformation percentage, and all other things are like this. So when you plot these two measures in x and y axis, so this is the layer thickness deformation percentage, this is the surface textural changes, you can find that there is a correlation between the data, and you can see that all the stable element data points are lying in a particular region, and all collapsed are lying in the another particular region. So by continuously monitoring this, we can able to see whether we are going to get a failure model or a good stable element. So conclusions is that I'm introducing two measures called as entropy standard deviation and maximum layer thickness deformation. There exists a correlation, so even you can use both these measures to substantiate the quality assessment that you are getting from one measure, and we are able to find a limiting value for both the metrics. And using this limiting value, we can actually predict whether there is going to be a buildability failure or not. And this can be used as a feedback into the printing system to actually stop. So to reduce the layer, the velocity with which the nozzle travels or the extrusion speed. So with that, we are able to increase the time for the bottom layers to gain some strength so that the further layers can be deposited on top of it. So this is a QR code to connect with me. Thank you.